All right. They still haven't fixed the clocks. Still says 9:30. I don't know why. Hope you guys enjoyed spring break. Sorry if I didn't make your day yesterday when I sent the mid-year results, the midterm results. We'll talk about that a little bit today. And then we'll also talk about, actually I've got the schedule right here. We'll do a Unix tip of the day, midterm. I'll have some comments about the midterm. I'm not planning on going over the midterm today. It's always a little dicey going over midterms in general because some people are like, this is boring, and other people are like, yeah, but we'll go over some specific problems probably on Wednesday. So there's a couple people who still need to take some parts of the exam, and I want to make it different enough that it's not, they can't cheat on it, but also the same enough so they can grade it fairly. It's kind of a little bit of a process. Many of you didn't know that there were actually mid-semester reviews that were online, or maybe you did and you didn't have time to fill them out. I did get some. I'd say they were kind of hit and miss. So I'll talk about the miss ones to some extent today. We'll go over a couple of the comments, because I think there were some very constructive comments about how we can make the class better. And so I'll talk about that. And then we'll go into today's discussion, which is on heaps, which is also what this week's lab is on. So like the last few slides today, pay attention to those, because the lab is specifically on kind of how to put together heaps, which is what we're going to talk about today. And we will we'll talk about that so you can get up to speed on doing that. Any questions before I start? Raise your hand if you still have trouble logging onto the grade website. Anybody still have trouble with that? Maybe you haven't gotten that email yet. The grades are published. If you didn't get an email from me, see me after class, and I'll point you to where the grade results are. Okay? And we'll go with that. So let's start out. Any questions? No? Oh, awesome. We'll start out with the Unix tip of the day. Let's see. So I think I may have mentioned this before. The next Unix tip of the day on Wednesday is going to be a slightly easier way to email yourself code that you might have like on the web server. If you want to actually email it to yourself, there's actually a built-in web email, or rather a built-in email system into the Linux thing, so you can actually email yourself with attachments and stuff. So it's kind of cool. But instead of putting together like 10 attachments, you can actually zip files using. We haven't done one of these yet, have we? I don't think we've done a zip one in class here. You can actually zip files as well. So I happen to have up here like one of the lab 5. If I wanted to zip up the entire lab 5 directory to actually send it to me, I could do this. I could go into the previous directory by doing cd ... That means go to the previous directory. And then I could say zip-r for recursive. It actually does the whole folder for you. Some name, let's call it lab5.zip. Hopefully I don't have that one already. Actually, doesn't matter. And then lab5, which is the folder that I'm actually working on. Right? And if I do this, it will take all the files in that folder and then zip them into my nice lab5.zip folder, or file, right here. And then you can actually drag and drop that, or you can email it to yourself, which I'll talk about on Wednesday, and how you can do that. So it actually allows you to zip up files, and so that you can keep them in one place. Like for instance, at the end of the semester, if you want to take back some of the, or save some space in your directory or something, and you might not want to see these assignments for a while or ever, you could either type rm for remove, or you could zip them up into a folder and then like email them to yourself or whatever. Okay, questions on zip? You can actually, zip has just like any other command, zip has about 1 billion different things you can do with it. So you can zip files and unzip them and all that. Questions on that? OK. All right. Back to the schedule. OK, midterm comments. So I saw, any of you guys Redditors? I don't know if you guys are. I saw this on Reddit the other day. I don't know if you can read that. It says, everyone go away. Right? It was this, somebody had a midterm and it was a terrible exam. You guys, as it turns out, did much better. This has nothing, me moving this up is only because I forgot to move it up. You guys did much better than 22% average on the mid-year. In fact, I was very happy with the mid-year grades. I'll show you a little histogram in a sec. Here's what they looked like. Of course, put that down. Hang on. Here's what it looked like. So This is not percentages. This is out of 78. You can figure the percentages out yourself, right? The average was a 65, which actually is about 80, I think 83, 84% average. Not too bad, all things considered. Yeah, it's out of 78. And if you didn't see the email or the post about that, I apologize. The grading program we're using, it's kind of new and still has some bugs. And it didn't allow me to automatically put the bonus points in. So everybody got 6 bonus points. Like it wasn't out of 84 or whatever I had it as, or was it 84, something like that. It's actually your tests are out of 78. So if you go online and it says it's out of 84, it's not. It's out of 78. Whatever the grade is, out of 78. The 5 bonus points were if you got the bonus points correct, and we'll talk about that. Kind of funny. OK, so we'll go over the other bonuses and things. So I got a couple questions about some of the bonuses. And we're like, hey, what's the actual answer? A couple of them you can figure out yourself. Like the one about what if you have raised the power 2 to the whatever power, what the answer was. You can actually code that up and figure it out yourself. But I'll go over that on Wednesday anyway. OK, if you were in like this range, you did very well in the test. If you're in this range, we might want to talk a little bit about how to improve for like the next test, like the final exam, OK? If you are in this range on the test, remember 2 things. Thing number 1, the test is not your whole grade. Certainly, okay, and midterms and exams for some people, I understand, are very difficult in general. So don't stress about that. If you had a bad day or whatever, talk to me. I will tell you this: if you did poorly on the mid-year and do really, really well in the final, I will weight the final much more than the mid-year. How's that sound? Okay, fair enough. If you did great on the mid-year, I'm not going to like take it away from you if you didn't. So we'll figure that part out. But just wanted to give you the basics of the grades here. Any questions on the mid-year exam? Again, if you couldn't see it online or whatever, let me know and we'll figure that out. I can always email you the PDF too. Anything? All right. OK, so as I said, there were some comments in the mid-semester feedback. I'm only going to take like 5 minutes on this. There were some good comments. There are only 22 responses out of like 180-something people. So 12%. So I am not taking this as like what everybody thinks. But the people who did take the time to fill these out, I'm taking your comments on board. As I said, there were some mixed reviews. And there are definitely some things I can do better to make this class better. We've still got a third of the semester or whatever to go. So I will take some of these considerations into I will consider a lot of these things and try to change them. But I won't make like sweeping, general, like huge changes. So I'm not going to just go and like make the whole class, because I have no idea how 78% of you or whatever thought, right? But here are some of the comments. OK, the lectures don't align with the programming assignments. And sometimes the relevancy of lectures isn't evident. I was familiar with dynamic arrays. So I think this is a fair comment. Like some of we've only had like 2 kind of big assignments so far. And they both focused on dynamic arrays and then some linked list stuff. And you might have already seen a lot of that before. So fair enough comment. The next assignments, you will start to get into some more, like we'll start to get into some data structures that are like a little more recent in the class. So fair enough comment. But I'll work on those, work on better assignments. Let's see. I think for assignments, we need to be required to write more of the basic code. And then somebody who said this said, the class is going to kill me if I say this. But I got this like 3 times, right? We need to write more of the code. There's a couple tricky parts about this. First of all, I don't want you to get bogged down in writing all this boilerplate code. I mean, that's part of the problem with C++ is you have to write a lot just to get up to speed to the point where you can write an assignment. However, I do think that's an important comment in the sense that, look, you do need practice writing some code. So I will, you'll see in some of the assignments, we're going to give you probably more leeway to write your own code. Okay, that is, don't let that scare you if you like were fine with the amount of code that you were given. But we will have more a little more ability for you to kind of practice your own thing. And by the way, nothing's stopping you from actually writing your own code. Like if you say, oh, he's giving us too much code, well, fine, go rewrite this part yourself if you want. I mean, if you want to practice this stuff, nothing is stopping you from practicing it. OK, all right, let's see. Provide doesn't go up until the night before the assignments are due. OK, look, fair enough. We haven't always put provide up exactly right, like a week and a half ahead of time or whatever. We'll work hard on doing that. But please, again, don't use that as your, like, is my program working, right? You should be able to tell that kind of on your own, right, by doing your own tests. OK, but fair enough comment. We'll work on getting that up a little sooner. All right, and this one, this was like the if you're a teacher, you got to take like criticism, and this one was like critical. But okay, so projects. Poorly designed, not very well thought out, disappointingly fill in the blank and artificial. So I know I'm like, then look, it's a you're welcome to your opinions on this. I just wanted to comment on the disappointingly fill in the blank and artificial. Part of the problem again is grading. How do we actually grade 200 assignments, right? Part of the problem with official is, or artificial is, well, we're in a class and we're kind of coming up with assignments that, I mean, they're not always going to be like these great assignments. I do think you'll like the last assignment that we're going to do of the semester. It is slightly less artificial. I won't steal my own thunder later. But from the standpoint of, I think you'll get a little bit more of that. The assignments don't seem to have much relation to it during class. I'm not sure I necessarily buy that. The labs, I think, well, I think this person also said something about the labs. I don't think the assignments I don't feel the assignments have been given so far have done much to help us understand the material we're learning. Well, I guess we will do better on getting better assignments to you in the sense of trying to kind of test your knowledge. At the same time, remember, this is a very large class with lots of differentiated students in here. Like some people who are like programming since they were 7, some people who are never programmed in their life before they got to Comp 11 or Comp 50. So I do want to take that into consideration too. But altogether, I mean, criticism and fair enough, I suppose. We'll definitely work on the last bit, trying to make the assignments a little more relevant to the classwork that's more current. Okay? All right, let's see. There are a couple more labs. Make the labs simpler. This one's a tough one. The labs are one of those things where, like, a lot of people were like, look, let us do more in the labs. Or then somebody says, make the labs simpler, writing our own simple applications. It's tough to do in a 75-minute lab. We're trying best we can. We've got a lab today that's another kind of, you got to fill in a few different parts of the assignment. But from the standpoint of, we'll see what we can do to get a little better on that. Let's see, what else? It's a lot harder to do in the lab. Requires us to understand other much more involved processes. Yeah, a couple of labs, I think like that maze one was probably particularly like tricky in terms of like what is going on here. And so I apologize about that. We'll try to make those better. Okay, and then let's see, more lab feedback. Sometimes field labs are very difficult to finish. I hope your lab leaders have told you, and I think I mentioned it a couple times, finishing the lab, while I think is important, is not really the absolute goal of the lab. The goal is to learn, to give it a good shot, and to do the best you can on it. But if you're not finishing like a particular lab, we're not going to like grade you on finishing and if it like perfectly works. That's not the point of these. Okay? Pre-make code as little as possible. That's a tough one too because of the 75-minute limit, and it's just tough to get labs that you can do in 75 minutes. So we'll work on it though. I will take these into consideration. Okay, and then finally, unify the lecture and labs a little bit more. I'm not sure I buy that the labs aren't unified. I mean, we're trying to do the lectures and then the labs follow on. The assignments, again, we'll test more data structures. We'll get to that. Okay, let's see. I think, one more. I hope there's not two more. Oh, there's two more. Well, let's see. This one, oh yeah, same thing. Look, what we're working on in homework is not what we're doing in class. If a lot of you guys think that, please let me know. And feel free to email me on either the regular email or the anonymous one as well. But okay, I get it. You guys are doing that. And then finally, please make the course more difficult. Again, tough to do because there's a lot of differentiated learning in here. Feel free to make the class more difficult for yourself. Get the A, and then do more stuff. Make a start project from scratch. You will see better projects in that sense. Don't cover as many specifics in class. I'm not sure everybody agrees that we're not covering enough specifics. Maybe we are. Please let me know. And then finally, this one's the big one that I would suggest to the teacher, that would be me, post links to things that we should read prior to class and make the class more philosophical discussion about computer science. I'm not sure this is really the class to do that part of it, unfortunately. There will be many, many computer science classes where you do talk about a lot of these philosophical things. But from the standpoint of I would suggest the teacher post links. I'm going to do that. Not necessarily before class, but definitely after class. So in the labs, you'll see links to other ways to get more help with the stuff. Okay? Questions on that? On the feedback? If you want to still give me feedback anonymously or otherwise, please do. I'm trying to make the class as good as we can, and we'll try to make it a little better. All right. Any other questions? Okay. All right. So let's get into what we're going to talk about for the next couple days and on the lab. Try to remember, well before spring break, when we talked about priority queues, and forget about that thing called a heap yet. We'll get to what that is in a minute. But we left off break talking about these things called, before break, talking about priority queues, which was basically you get this object and you can query the object for the highest priority item, whether it's the lowest number or the highest number, depending on how you build it. And then we built a couple of them. And we built a couple of them using sequences, like regular old arrays, or dynamic arrays, or whatever. And we found there were some trade-offs here. Okay, remember, for an unordered list, inserting, very easy. You just throw the item at the end, and you're done. Right? Order 1. Min element. OK, for an unordered list, you've got to walk through all the elements to find which one the minimum is. In fact, you have to walk through every one. You can't even stop anywhere. You might be the last one. So you have to do that. That's going to be an order n sort of behavior. And then remove min. Well, you first have to find it, and then you have to remove it. We talked about a couple different ways of removing it, which makes it easier that you only have to go through the list once, and then remove is relatively easy. But you still have to find the minimum before you can remove it. OK. Then we had an ordered list. Okay, and in an ordered list, we said, all right, while we're inserting, we're going to order everything. Well, the inserting part, right, takes order n, because you have to go through and find out where to put it, and then move everything. Right? So you find where to put it, and then move everything sideways, and then you plop it right in there, and that takes, you have to go through all the elements to do that. OK, then we've got the min element, easy. You know where it is, it's right at the end. Boop, you grab it, you're done. Remove min, same thing. You know where it is, you remove it, you just change an index, and you're done. Okay? But those are the trade-offs. All right. And then I said standby. And I almost gave you a heap question on the mid-year. Bruce talked me off the edge, or the ledge on that one. It's part of it is sometimes it's kind of fun to give you like challenging stuff on mid-years, but stuff that you'd like never seen before probably wasn't the best idea, which wouldn't. Although it makes you really think about it. So anyway, OK. So what we're going to do is we're going to talk about a different way to build a priority queue by using a data structure called a heap. Now, some people, I think in the last class, actually said, hey, can we just build a priority queue using a binary tree? Right? Sure we could. We could build a priority queue using a binary tree, right? And what it would be is, let's make a quick binary tree, right? Let's say we had 10, and then we had 12, and we had 11, and I don't know, 15, and then let's say 6, and 7, and 2, and 1. That's a proper binary search tree, right? OK, could we find the min element in this? Sure, what was the order to do that? Do you remember? Depends. I kind of asked that in a strange way. What's the worst case order? You remember? Order n, because it could be a linked list. Yeah, my thing's done. It could be a linked list, but on average, we're going to get a nice log, like log n, to get to the minimum value, right? So we can do that. We could do a priority queue using this, OK? But there's actually an even better tree structure to do this priority queue with, and it happens to be called a heap. Okay? Here's what a heap is. Okay? It is also a tree like this, right? Except all that it is that the children have to be smaller than any parent, and than their parents. Okay? Or I guess I should say, the children should be either smaller or greater, depending on how you're actually making this heap. Okay? In fact, we'll do it the other way to start out with. If we had, I guess I should have left the numbers up there. If we have a heap that has let's say 1 at the top, right? Well, in this case, all of its children will actually be greater than it, because the minimum one is going to be at the root here. Okay, so if we put some more elements in here, right, like 7 and 14 or something, right, both greater, okay, anything here has to be bigger than 7. Both the left and the right has to be bigger than 7, right, like, I don't know, 16 and 9 or something like that. And then everything here has to be bigger than 16, like 22. And then over here, everything has to be bigger than this, 19, and 40, right? This is a heap structure. Okay? This is actually called a min heap because the minimum value is at the top. Okay? And again, all that we care about is that the children are either less or greater, in this case greater than the parent. Okay? Parents have a higher priority key than all of their children. And notice there is no like specific ordering like a binary tree. Okay? You don't have to worry about that. All right. Here's the two different types. Okay? We've got min heaps and max heaps. These are for binary trees. A heap in general can have more than two children if you want. There's lots of different types of heaps out there, but we're going to focus on the binary heaps. Okay? And you've got min heaps and max heaps, and again, all it is one, the parent has a higher priority than its children, whatever higher priority means in this case. Okay? All right. No implied orderings. Both of those are heaps, even though they don't look right because you're kind of in the mindset of binary search trees, right? But they both are min heaps, in fact. Okay. All right. Heaps are completely filled. Okay, here's what we mean by completely filled. I've talked about this a couple times in here. Okay, what it means is that you can't have any extra spaces. So is this completely filled here? Actually, it is. What it means is for the number of nodes, okay, I know, I'm being tricky here, right? For the number of nodes, if you go along and do all the nodes and you get to the last one, it's got to go in the leftmost position in the last part of the tree. Okay? These are actually kind of empty, right? I'm doing them up here with little like boxes, meaning they're not even filled. They're just kind of there, right? And you've got it's got the maximum number of nodes, and the internal nodes, that's the ones that are the ones that are actually filled, are left of the external nodes if there are any left. You could have these all filled. Sure, you could certainly have all these filled, but you don't have to. And if you don't, you just have to remember you've got to fill from here to here. Here's a question for you, and this may come into play later in the lab today or tomorrow. If there is a right child, does that mean there has to be a left child? Yes, right? You can't have any right children without also having a left child. Okay? All right. Do you remember, I think this is the next, yeah. Do you remember when we talked about complete trees before, how we were able to set them up in memory? Remember we could do it with a linked list. We could certainly do this with a linked list. You remember the other way we did that? An array, right? Yeah. This is how you can represent a heap with an actual vector or an array. I guess I should say an array. All right? Yeah, in this case, I mean by vector, I mean array. Okay? Sorry about the black type here. All right? Before, we had done this before, and we said, let's just make the root right here. Well, that's one way to do it. Okay? As it turns out, heaps are, in general, not always, but in general, heaps are actually set up such that the root is actually at position 1. Now you go, oh, you spent all that time telling us about position 0 and how everything's 0 indexed in computer science and all that. Now you're all of a sudden coming up with some data structure that actually you stick the first element at position 1. Here's the reason. Before, when we talked about it at position 0, remember how, you may not remember this, but in order to find the children, you had to do like 2n plus 1 and 2n plus 2, right? Well, as it turns out, the math is just a little bit easier, and there's a couple other reasons that we probably won't get into, but the math is just a little bit easier in terms of finding the various parts of a heap. So, for a heap, if the element is at position I, then the left child is at 2 times I. Ooh, that's easy, right? You can easily do that. In fact, computers are very, very good, by the way, at multiplying by powers of 2. Anybody know how they do it? It's like an advanced topic. How a computer would multiply by 2? Yeah? You would actually just add a 0 on the end of the binary number, which, like, let's say you had 1, 0. Not a terrible piece of chalk. Let's say you had 1, 0. right? Anybody remember what that is in binary? 1, 0. This is the ones place. This is the, so this is a 2, right? Right, 2. And if we wanted to make it 4, we just add another 0 on there. And that makes it 4, right? Well, as it turns out, okay, doing that is easy. You just shift the 1 over and add a 0 at the end. And it's called a shift. And so multiplying by powers of 2 are really easy. If we wanted to multiply this by, like, if we want to multiply it by 4, we would shift it over 2 more, like that, right? And that actually multiplies by 4. So it's very easy to do. So if you're talking about heaps and you want to like maximize the ability to say find your left child, well, multiplying by 2 makes it really easy to do. OK, the right child. Well, the right child is going to be at one more location past the left child, right? So it's just going to be 2i plus 1. Fair enough. OK. And then the parent in this case is going to be at I divided by 2. And these little guys mean the floor function, which means take an integer division and just chop the end right off the integer division. So for instance, if you look at 13 over here, its parent is 8. Well, 13 happens to be at position 7. 7 divided by 2 is 3.5, right? Which is just 3, right? So if we go down to 3, there's 8, and there's the parent of 13. OK, you just take the integer division and do that. Computers are also very good at that. They just shift the other way, right? In fact, if they just shift the other way to divide by 2. And in fact, if this was a 1 or a 0, it automatically just shifts it right away. It doesn't actually matter. So again, kind of a way of speeding things up a little bit in order to do this. Okay? We've also got the heap size, which is just the number of elements. And in this case, notice something about this. There's 8 elements here. There are 9 elements here. And the last element is at the index of the heap size. OK, so keep that in mind for the lab later today. When you're trying to, say, insert one to the next one over here, it's at the heap size plus 1. Kind of different than the way we've done it in class in some other structures. OK, questions so far on this? No? Good. Stuff's fairly straightforward stuff. OK. Now, why do we call this a heap versus a priority queue? So the priority queue is kind of the abstract like structure. In this case, we're talking about the actual data structure behind the scenes is what's called a heap. You will see them interchanged a lot. If somebody says, oh, I'm going to build a heap, think priority queue, right? It's basically the same idea. But when we talked about priority queues, now we're going to kind of switch over to thinking of them as heaps in this case. Okay? And remember, you can make a priority queue in lots of different ways, which we did. But now we're going to do them with heaps. And it turns out it's such a good structure that you almost always really want to build them using a heap. OK, so remember there's 3 different things we have to do. We have to find the min element. We have to insert an item. And we have to remove the minimum. OK, remove the smallest item. 1 and 3 could also be maxes if we're doing max heaps as well. OK. Now, let's take a look. I'll leave this up here while people are writing it down. OK. Where is, here, I'll remind you guys, where is the min element? It's at location 1, right? So how easy is it in a heap to get the min element? It's easy, right? To actually return the min element, it's easy. It's order 1, absolutely. And it's really easy to do. OK, you just return the first value. Now we've got to talk about actually inserting some items. Okay, and we'll go into this in a little bit, but I want you to actually, I think we have some time to actually kind of think about this before we jump into it. OK, if we're going to take this heap here, okay, and we're going to insert an item, like some random item, right? Where would a good place to put it be? There's probably 2 real good choices. What do you think? One that's real, that's one that's like the choice, but I would accept 2 answers for like possible choices for this. Where's a good place to put some random element straight off the bat? The end, which would be here or here. This one, right? If you put it over here, you'd totally mess up the fact that it's a heap because you'd miss out on all these other elements in the middle. OK, so I like the idea of putting it here, right? Where else might I have accepted a good answer for? Maybe? Yeah. Well, what if it is the min? Yeah, why don't we just put it at the top? That's not, I would have accepted like putting it at the root as well, right? The only issue with putting it at the root is, well, you got to figure out where to put this one, and then you got to figure out where to put all those. Now, if we put it down here, and actually, Danielle has a good point. What if it is the minimum? Let's say I inserted 0, right, which happens to be the minimum here. Have we retained our heap as an actual heap? We have the rules, right? The rules say every parent has to be, in this case, less than its child. So now we've messed this heap up. So we have to go and reorder things. Any ideas how we might reorder this? Yeah, Hobby. There you go. So maybe you can check the 16 and the 0, and you can say, okay, are we going to swap in this one? Yes, we are. Why? Because, well, now it would be in the right place there, right? 16 and 0. Besides the rest of this, is this part from here down a priority, or a heap rather? Sure it is, right? Start thinking maybe recursively, right? Because we're going to have to do that for each kind of one up here. We're not done, of course, yet, right? But from here down, we're good. Could it have been the case that if there was some other number here, let's say in this case it was 16 and 0, could it have been the case that some other number here would have upset the order of the queue, or the heap, if we actually replaced them? Yeah, why not? I see a bunch of heads shaking, but could we move this one here, and then somehow this one's now out of order? Yes, Brett. Yeah, as long as you've got a heap before. So Brett says, look, before you do the insertion, it was definitely true that this one was, in this case, less than this one. And if you're all of a sudden replacing with something that by definition has to be less, it's going to also be less than this one. OK, so there's no way to have to worry about going back down the tree in some other way to do this, which is kind of cool. OK, oops, 0 and 16. We're not done yet. Now what do? Yeah, we do this. What we're doing here is actually what we call bubbling up, right? 7 and 0. And then we're not quite done yet. One more bubble up here, right? 0 and then 1. 0 and 1. And now we're actually done. OK? That's called upheaping or bubbling up. There's probably other phrases to do as well. But that's how you actually do the insertion. OK? Kind of a neat little way to do that. And what would the order of that be? What would the asymptotic behavior be for doing that? Any ideas? Yeah. Yeah, in fact, it actually is log n. Why? Because the maximum number of times you're going to have to go up is the height of the tree. Because this is a complete tree, what do we know about it? What do we know about it because it's a complete tree? Yeah, Brett? Yeah, the maximum height is balanced, right? We know that it's got to be balanced. I mean, the only thing that might not be balanced is this last little level, which we don't really care about in the asymptotic notation. It's going to add a factor of 1 added on, which is not going to actually make a difference. So absolutely, it's going to be log n behavior to insert. Kind of cool. Okay. All right. While I've got this up there, I'll let you guys think a little bit more. How would I remove the minimum element? This one's a little bit trickier. Okay. How do we actually remove an element here? You already answered a bunch. I'll let you answer if no one else can think of it. Other ideas about how to actually remove an element? You've already answered a lot, Brett. Start with the middle. I don't think I've heard of middle person in a while. What do you guys think? Yeah, go ahead, Elaine. Yeah, you'd remove the root. OK, I like that. Because, in fact, a lot of times when we do a remove min, we actually return the minimum. Depends on how you build it, right? So that one's gone, right? And now you're saying, well, bubble up. Where would you start? Why the left child? So in this case, it happens to be this one, which is the one that we want to end up at the root, right? OK, so that's when we want to end up at the root. What if it was over here, right? 1 and 14. Would that wouldn't quite still be it. Let's say this was, I don't know, let's say this was 6. All right. That would be close. Now we still want to get the 1. So if we start over here, we'd go all the way bubbling up, and then, well, then we'd have to somehow get this one up. So I like the idea, not quite the way we're going to have to do it. Yeah, go ahead, Eliza. You could do that. Yeah, you could compare the roots children and push up whichever one. Let's see if that would work. Let's say we had, I'm going to mess this up here. It's going to, let's say that this whole side was, I can't even think about that. The problem with that, okay, is that you might compare the root, but it might be something down farther which might end up being the problem. And that actually would work, except that now you've got, I think that would work, except now you've got to have to do the same thing with this one. So you could do that. That's actually not a bad idea. Yes?
Would you take the farthest down on the right and then put it on the top so you know that all the nodes are in the right place?
Ah, that's a very good point. Yeah, here's the other issue with what you'd said. I like what you'd said. If we had like compared here and then compared these guys up here, right? Let's say that this one would end up here and then this one would end up here. We've got a problem, right? This one is now an empty node. Like that's exactly the reason, right? So if we had done that and put the 1 here and the 19 here, okay, well now we've got a problem like which one do we put here, right? Well, we could grab this one, but then that might mess up this side of the, okay. So, but we're getting there, and I really like what your idea was over there. In fact, that's actually the right answer. Okay, here's what he said. Let's see, this was 19 and this was 1. You're taking a node out. So at the end of the day, right, you're taking a node out. At the end of the day, you'd better have this node missing, right? Because we're going to have to continue, it has to remain a complete binary tree, meaning that there's only going to be, instead of 1, 2, 3, 4, 5, 6, 7, 8, 9, there's going to be only 8, right? Did I count right? 1, 2, 3, 4, 5, 6, 7, 8. You're going to go from 9 to 8, right? And so what you want to do is you want to make sure this one's gone. OK, so I like that idea. Just get rid of this one and say it's now up here. OK. Now what have we done? Brett? Yeah. There you go. Now you can do a bubble down, which is exactly what Brett said, right? You can now bubble down, right, 16 here, and you can actually do that. Now, as it turns out, we're going to do it slightly differently, okay? Well, actually, we're not. We're going to do that. We're going to bubble it down. 16 would be switched with which child? 1, okay? And then, so that's one comparison we would have to make. 1 goes there, and 16 goes there, and everybody's good except for, let's call that a 14. I don't remember which one it was before. Now what do we do? Do the same thing again. So it's a recursive kind of idea here, where we have 14 and then 16. Have we retained the heap or gotten back our heap property? Have we made sure that it's complete tree? We have. Okay? So this bubbling up and bubbling down, or upheaping and downheaping, is going to be really important to this algorithm. Okay? And you'll practice at least the downheap part on the lab today and tomorrow. Okay? Questions on that? All right, let's look and see if we got it right. Heap operations, min element, order 1. Definitely, it's easy to do. Just remove. You don't even need to remove it. You just return it. It's the root. Well, it's position 1, not the root. I mean, it's not position 0. Position 1. Okay. That extra, you might complain, by the way, that hey, you're wasting space here. Yes, we're wasting 1 element. Waste, kind of. I mean, you're still, like, what's the maximum number of nodes that could go in here in this before we go to a whole other level? Remember what it was? It was 2 to the n minus 1? Or did I do it right? Yeah. So in this case, it's going to be 15 total here. And there's actually goes up to number 15 here, even though there's 16 items here. So it's actually kind of nice in the sense that it works out and we're not really wasting much space. Powers of 2 are always a good thing in computer science. Okay. All right, so let's see. Okay, that one was order 1. Insert, we said we start inserting, and this is the mechanics of it actually. Insert the element at heap size plus 1. Okay, this probably destroys the heap property unless you got really lucky and it was all the way on the bottom of that side of the tree. And then you perform this bubble up or up heap by comparing the added element with its parent, and if it's in the correct order, you stop. Once you get to the correct order, no need to continue anymore. Like if you don't have to make a swap, you don't have to continue and check the next levels up because you've automatically guaranteed that it is back in the heap, back in a proper heap. Okay. All right, and then if it's not in the correct order, swap and repeat step 2. So it's this recursive behavior again. There is an animation which I'll show you. Actually, I've got another one. Let's see. Back to the thing Brett told us about. This is a nice min heap representation here. You can go to this website. It's on the thing about it. And if we want to insert things, right? So let's insert 5. Let's insert 5, and it just shows you there. And then insert, I don't know, 22, right? Like that. And then let's insert 4. Insert 4 is going to go over there, and then we're going to have to swap because it would be the wrong order. So relatively straightforward, this bubbling down sort of thing. Okay, and you can go look at this, and we'll get to another one in a sec, which is kind of interesting as well. Okay. Let's see. I think I do a whole bubble up here. We just did this as well. But if I insert 9 there, I have to swap it with 11, then swap it with 10, then swap, and I'm done. Once you get to that point, you're done. Okay? You're bubbling up. All right. And keep in mind, when I say insert 9 in the element, remember the 9 is just the key. It's just the part that's telling you what the priority is. It's not the actual stuff that we care about. Okay? We can drag along whatever we want and prioritize by those keys. It's a kind of an important one. We're always dealing with like integers here, but the stuff that gets prioritized is kind of dragged along. Okay, and then, so the worst time complexity, okay, is order log n, which we talked about. Okay, I mean you have to bubble up here. It could take all the way up to the top, but a log n sort of steps. Not too bad. As it turns out, average complexity, and how they determine average is if you are inserting like random elements. Average complexity is actually order 1, which is really cool, right? That's actually really cool. And there's a paper you can read on it, like from 1976 or something, that goes into a little bit more detail. But if you want detail on that stuff, go ahead and read it. Okay, it's cool how it's a lot of math. So if you mathy types, go read that paper and you'll see, oh, this is kind of neat, how they actually do proofs of what the average behavior is. That paper is also a good idea, or a good way to show you why I don't ask you to do average ones, because it's like 12-page paper or something like that, right? Talks about it. But anyway, point is that inserting into a heap also very fast on average. Great. Okay. We talked about remove min as well. Okay, remember we take the last element, we return the element at the root, and then we take the last element, swap it, and then bubble it down. Okay. Here's the part that's a little tricky from the standpoint of doing this for real, which you have to do in the lab, right? Okay. First, you compare the root with its children. Okay. Remember, sometimes a child might not exist. Okay. Let's go back here for a second. If we did something where we were going to check this one with its 2 children, right? First things first, you better make sure that this right child exists, right? Because if it doesn't, then you're going to be comparing against who knows what. Could be 0, could be some other random element, doesn't matter. First, you have to make sure that it actually exists, okay? Then you can actually do the check. Remember this. If the right one exists, you know the left one exists. Not true the other way around. You can't just check the left and assume the right one exists, okay? But you do have to remember to do that check. You'll get some practice in the lab on that. Okay? All right. So let's see. Swap with so bubbling down, compare the root with its children. If it's in the correct order, you're done. Great. And we know that it's still got the heap property, and it's actually fine. If not, swap with the smallest child and then repeat step 2, doing this recursively. Okay? And again, you can do it recursively or with a loop of some sort, but recursive is probably easier to think of. Okay? And then make sure you check, see if those children are proper. Okay? All right. And here's just the example. If we're removing 5, 5 is gone, and then we take 13 and blast it up to the top, and then bubble down. Compare to your children, compare, and swap, and you're done. Okay? Any questions on that? All right. What is the asymptotic behavior for this? Any idea? Asymptotic behavior for removing the minimum. What is it? Log n. Why is it log n? Yeah. Remember, doing the removing the front one and taking the last one and pushing it up to the top, those are constant things. You can do that in 2 instructions, right? You get rid of this one, and then you move this one up into here. Okay? And that's it. Now you've got to do the bubbling part, and that could be on the order of, oh, I got to bubble it all the way down to the end, or in this case, all the way down to the bottom again. Okay? So that's what you need to remember. Okay? And again, a lot of times it's not order log n, just because of the, well, in this case it's a little different because this is going to be one of the higher ones, right? Because it's at the bottom. Yeah. Okay? All right. Now, let's talk about how we would actually build a heap, right? From scratch, I mean. Okay? What would the best way to be to build a heap? Well, can think of some ideas of how we would actually put this into the array to start out with. Think about that for a second. What do you think? How are we going to build this into our array from scratch, such that it ends up as a heap, of course? Yeah. Yeah, you could do that. You could find the minimum element. So you could walk through and you could go, OK, let's see. 8's the minimum. Let's put that in first. OK, and then you find the next one, right? And you go through and find the next one. What would the order be for inserting that, for doing it that way? It would be, be careful. Let's say that it was 8, 9, 10, 11, 12, 13, right? You'd go and find the minimum, and then find the minimum again, and find the minimum again. It's kind of like order n squared, right? I mean, there's a couple, it's not quite that bad, because you are putting it in as you go, right? But that's an idea. That's a good idea. What's another? What can we do it using the tools we already have for making a heap? How are we going to do it? Just insert in the order. Yeah, exactly. You could do that. You could say, let's put 14 in, right? And then 14 goes here. All right. And then we put 9 in, and 9 goes here because it's a heap, right? And then we have to bubble up in this case, right? 9 and 14, so we have to swap that, right? 9 and 14. And then we put in 13, and 13 is going to go here. And we can bubble up, but there's no need to, right? And then, let's see, 43. Oh, that's a nice one, too, it turns out. OK. Good idea, right? Very good idea. And then we use the tools we already have for this, right? OK, what's the asymptotic behavior for that little maneuver there? Any ideas? It's the first one we've seen of this one, I think. Yeah, Ben. Ben says n log n. Can you walk me through your idea of why it's n log n?
Because it's every insert is log n.
Every insert is log n on average, or well, worst case, right? On worst case, everyone. OK, and?
Worst case, we have to do log n times.
Yeah, in fact, you have to do, well, right. You have to do n times. You have to get through all of these things. OK, so this one is one of the first ones we've seen where it's order n log n behavior. OK. Question is, can we do any better than that? That's a pretty good one. Order n log n for insert to making a heap, not too bad, right? I see some wheels turning back here. Any ideas of how we might be able to do this? I wouldn't have necessarily thought of this myself. I'm not sure when this one was discovered, but ideas about any other ideas? How we might do this a little more efficiently? Back here? Yeah. So let's see. So you're saying if you could put 14 in here and then make 9 the parent of 14. Really what that does, think about it. Remember, we've got to do, if we're doing this in an array of some sort, right? Let's say you put 9 here. Well, yeah, you could do that. But if you want to make 14, like you want to move 9 here, you're really doing a swap. So it's pretty much the same idea. Yeah, pretty much the same idea. But you're getting there. It's a good idea, good thought. OK? Yeah? Morgan. You could sort the list first, then insert it. Sure, you could do that. It turns out that sorting is also order n log n. Best we could do for sorting is n log n. So close. But that's not, we could do that. Sure. Yeah?
Just find the lowest, the min element, and then just put everything else in it. It doesn't matter.
You could you find the lowest element and put everything in, it doesn't matter. Let's find out. I'm not sure this would work this way. Let's find out. So it turns out the minimum is, what is it in ours, 8? OK, so what you're saying is find the minimum and then just kind of fill in with any other order. Let's see, 14, 9, 13. We're kind of in trouble on that one. But I do like the way you're thinking, right? I like the way you're thinking that says, just put them in there and then figure it out. OK? That's not a bad idea. All right? Just throwing it in, yeah. Could you put them in the, oh, that's a really interesting idea, right? Put them in the index of like where they actually would fit index-wise. That's actually a completely different type way of sorting elements, which is actually kind of fun. You're saying, look, these elements can only go up to some number, right? Let's make enough space for all of those and just throw them in their proper place. So this one would go in it would go in index 14, and this one would go in 9, and that one would go in 13. That's a really fun way to do it. What's the problem with that? Yeah, like all of a sudden I do this, and then I have like 2.3 million, right? And all of a sudden there's like, I'm like, oh boy, now I've got, all of a sudden I've got a huge amount of space. What's interesting about that is, if you do it that way, right? It's actually, I believe, called a bucket sort. Okay, and if you do it that way, okay, what is the order of the sort? Like, what's the asymptotic behavior of that kind of sort in time? N. Yeah, I lied to you a little bit. I mean, I guess I said, look, sorting is order n log n, right? If you're willing to give up enough space, like up to the maximum amount you have, and there's no duplicates or whatever, you can actually sort this in order n, right? But that like space part is the big problem, right? Where all of a sudden you're like, oh my gosh, I'm done with that. Yeah.
You just put everything inside first and bubble down from the views.
Bubble down from which ones?
So you could just build a tree in order from 14 to 12.
Yeah, just build the tree in order. That's what we're going to do, absolutely. And then what are you going to do?
And just start go down from 14 and package it instead.
Yeah, you could start bubbling down from the top here, right? It's not a bad idea, not a bad idea. And we're like this close away, okay? You're this close away. You might end up overdoing, like you might end up in your way doing it that way. You might end up like redoing things that you didn't want to. Like you might end up not getting to the right place. But I like the way you're thinking. Okay, let's walk through it this way. Okay, we could do this. We said that was order n log n. Okay, here's the better way that I think you've almost landed on. Okay, if we insert all the elements, okay, that takes order n behavior, right? All right, insert all, and then starting from the lowest completely filled level at the first node that actually has children, which, as it turns out, is position n divided by 2. Okay, right? Bubble down. I know this one takes a little. You're like, what's going on? I'm going to show you what's going on with this one. Okay, down heap each element. First of all, you have to believe me when I say, or you have to figure out, when I say that position n divided by 2 is actually the first node that's going to, and n, by the way, is the total number, the heap size. Okay? Heap size divided by 2 is actually the first node that has children. Right? 1, 2, 3, 4. 1, 2, 3, 4. 4 divided by 2. 1, 2. This is the first one that has children. Okay? It actually works for every single one. 1, 2, 3, 4, 5, 6, 7, 8. Right? 8 divided by 2 is 4. 1, 2, 3. 1, 2, 3, 4. This is the first one that has children. It actually works every single time. Kind of cool. Okay? You're doing integer division, yes. Yep. Yep. N divided by 2. Right. In all that other stuff, it's all integer division. Which, by the way, is why we make you take that math class that only has that only deals with general integers, right? Right. Discrete math. Okay. All right. So here's the example I'm going to show you. All right. Same numbers we had before. Just throw them into a heap. Don't worry about the fact that it's in the wrong order because it's not heap yet. What we're going to do is we're going to heapify this. It's actually the term they use. They call it heapify. All right? All right. So we start at heap size divided by 2. In this case, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 divided by 2 in integer math is 4. Right? So this is the first one that has children. Start here and down heap that one. Okay? Start there and down heap that one. All right, so let's see what we're going to have to do. All right, we're going to have to take a look at this one and compare it to its two children. That's how we down heap, right? And we're going to swap it with the one that's the lowest. And that will retain the order. Okay. All right. And then we're going to just go backwards. We're going to be kind of walking, like our loop is going to be backwards now. We started with, did I miss one? Which one did I miss here? I must have missed oh, no, I didn't. No, I didn't. No, I didn't miss one. It goes this one, and then the next one in reverse order is this one, right? And then we're going to go to this one, and then we're going to go to this one, right? So you're going to start at the one with the children, and then you're going to check and see, and you're going to swap if necessary. Then you're going to go backwards and go to this one, and then you're going to down heap this one. And down heaping this one and why is this always going to work? I mean, why are we, you'd think, oh, we're missing some things. We might end up with the wrong thing. No matter what, right, if we swap this one with its lowest child, first of all, we know that these ones don't have children yet. And if they did, we would have already taken care of them and put them in the right heap order, right? And then this one happens, and this one, if we swap it with the one that's the higher priority of its two children, in this case the 8, then this one has to be higher priority than that one. So it does work. Okay. All right. And then we look at the number 2, which we compare to 12 and 10. Okay. And there's nothing needs to be done for this one, right? Because it's already in heap order. You can't stop with this yet, though. You can't say, oh, now I found one that doesn't matter. You can't do that. For this, you have to heap. You have to do all of it. Okay. And then we go to the last one where we have 14 and 8. Swap them, and it is, and we're done. Okay. Well, we're not quite done. We're done in the sense that we've swapped that one, and then if it has children, right, you do have to continue to down heap for the full down heap. In this case, we're going to swap the 14 and the 11, and then we'll be done. Okay. Cool. All right. Now, oops, I didn't actually talk about the order of this one. We don't actually have to, well, is it still going to be order n log n? Still going to be order n at least, because you got to stick them in there, right? Then the down heaping is where it gets a little bit tricky. It turns out it is, I guess technically it's still order n log n, but it's better than the one we tried before where you're just inserting it in there. There is a factor there that that's going to make a difference. Okay? It's actually kind of mesmerizing to see it in action. Hang on. This one here, if I build a heap, right, and I speed it up, right, actually you can see it. Well, no, you can't. Hang on. Let's try this again. I won't make it go quite as fast. There we go. All right, so let's see. I'll make the animation speed a little bit less, and then build heap. All right. So you can see it started. It turns out that this is a full tree anyway, but it started at the one with the children, the first one with children, and then it has to just do all the down heaping for each one. Okay. All right. That's how you heapify a list of numbers. Okay? Once you heapify it, right? Once you heapify it, how do you get a sorted list out of it? Once it's heapified, how do you get a sorted list out of it? Ideas? It's actually pretty easy. We talked about this way back when we did priority queues. What's the way how do we get the sorted list out of this? Yeah. Just keep removing min, right? It's going to remove the 1. Then the 2 is going to bubble up to there. It's going to have to remove the 2. Then it's going to remove the 3, and then 4, and so on, and so on, and so on. Okay? Pretty simple stuff. All right. All right. So that's heaps in a nutshell. Okay? Now, this week's lab. Just going to go over this real quickly. You're going to have to do three little things, right? First, you have to do build heap, which is what we just did. Okay? The nice thing about build heap is that you can use the other properties. To build it, you just have to insert everything in. In fact, I think the program already inserts it for you into the random order. Then you're going to have to do remove, right, which removes the min. Then you're going to have to do down heap. This one's the harder one. Okay? And don't forget that the root is at location 1, not 0. That can screw some people up a little bit. This one. Okay? For build heap, okay, you're going to get the heap built already for you. And then remember, all you do, start from heap size divided by 2, call down heap on it. And then loop. Right? Loop backwards. Okay? And you got to remember where to stop that loop too. Don't go too far. Right? Okay? And then removes the minimum item. To remove an item, you return it, and you have to do this down heap business, okay? Where you have moved the last item up to the top and then down heap it. Okay? And that will end up with the right, everything will be in heap, it will still be a heap after that. Okay? And then finally, we've got down heap, this is the tricky one, okay? The other ones aren't too hard to implement because you've got down heap already, right? Or you've got I guess you've got up heap and you've got down heap already. In this case, here's the algorithm. Remember this. Determine if there's a smaller child. Swap the node with the smaller child. It's that determining part that you got to remember to do. Okay? And then recursively do that. Okay? All right. I think, so I promised you some references. Lots of references here. The Wikipedia article on binary heaps is actually pretty good. If you just go and look at heap, it's not as good, right? There's an article in Wikipedia about heaps. The one on binary heaps is actually I think, more detailed on how to do these sorts of algorithms. I showed you the visualization already. You can take a look at that. Our book. So I barely even mentioned our book in like the whole class, right? Okay, our book, page 540, 545. It's all right. I'm not a huge fan of our book before. I mean, it goes into some details that I don't think are really relevant for this particular class. If you want more detail about some of the other math behind it, there's a very good YouTube video. I think it's in MIT OpenCourseWare or something like that on heaps, where he does max heaps instead of min heaps, but same ideas for everything. And you could look at the video on that. Okay? All right. Questions on heaps? Anybody have anything else? No? Any comments on the midterm or on the reviews or whatever? As I said, feel free to email me anonymously or otherwise. All right. Let you go a few minutes early. I'll see you in lab Wednesday.